effect some fundamental aspects. Excuse me. Okay, hydrogen spillover is related to hydroconversion processes, an important class of reactions, which is catalyzed by oxide-supported metals and also by metal oxides. This talk takes illustration from hydrogenation, dehydrogenation, and hydrodeoxygenation reactions. Hydrogen spillover, I recall, is the dissociation of H2 on the metal particles, and the H atom formed can be stored on the support or react in hydroconversion reactions. About spillover hydrogen, there is many questions and controversies. Main questions are, what is the mechanism of formation, the mechanism of diffusion of hydrogen spillover? Does exist correlation between structure and reactivity of H spillover species? What are the reaction paths in hydroconversions? And in this reaction, what will be the role of oxygen vacancies? In the literature statements are incomplete, wrong, or even correspond to misunderstandings. To understand, to comprehend hydrogen spillover effect, we have to get back to hydrogen activation of metal oxides. For reducible oxide, it is well established that it consists in the reduction of the support, then the dehydration of the support, giving rise to sites for the accepting site for hydrogen. For non-reducible oxides, there is a process of dehydroxylation. In both cases, hydrogen is incorporated as HOH pairs. After evacuation with reducible oxide, we obtain an oxygen vacancy stabilized by an oxygen atom negatively charged. For non-reducible oxides, there is a formation of a surface metal cation also stabilized by an oxygen atom negatively charged. Finally, during activation of metal oxides, we form conjugated sites, HOH hydrogenizing sites, and oxygen vacancy or surface metal cation hydrogen receiving sites. What is the mechanism there? Now, what is the mechanism formation of hydrogen spillover? The literature statement is that hydrogen spillover is thermodynamically allowed for reducible oxide, but none for non-reducible oxide. This is wrong, and we have established this previously in a review. The mechanism for reducible oxide support is, as I said before, the reduction of the support and its fast propagation all over the support, far from the metal particles, forming the receiving site for hydrogen after dehydrogenation. For non-reducible oxides, there is a dehydroxylation process giving rise to a hydrogen atom at the interface. And after that, we have a set of consecutive HOH exchange reactions leading to the coverage of the support by H atom up to a maximum determined by the activation condition. So for non-reducible oxide, hydrogen spillover does exist. It is also thermodynamically favored. Now, what is the diffusion mechanism of hydrogen spillover? The literature statement is that it consists in the hopping of single H atoms from OH group to OH group of the support. And this is generally demonstrated by a hydrogen deuterium exchange reaction. The deuterium atom migrate from OH group to OH group. This is untrue. This is wrong. Our model is that after evacuation, hydrogen spill over from the metal particles form HOH pairs at the interface, and the H atoms migrate to the neighboring receiving site for hydrogen, and these all over the support for reducible oxides. A similar mechanism exists for non-reducible oxide support. In effect, two H atoms, two spillover H atoms, form at the interface HOH pairs, which then gives rise to the migration of the H atom to the neighboring receiving site for hydrogen all over the support up to a maximum depending on the activation of the catalyst. So the migration is a diffusion of two H atom pairs. An experimental verification was given by Dupré in 1997. It consisted in the determination of the coefficient of hydrogen surface diffusion on rhodium catalyst deuterium exchange reaction. The coefficient of diffusion was determined as 75 degrees, and the catalysts were activated under H2 at 450 degrees C and evacuated at the same temperature. From the table, it results that this coefficient of diffusion decreases from ceria to magnesia, then to silica. The prostate acidity of the catalyst were determined, and as you can see, there is no correlation between this coefficient of diffusion value and the prostate acidity. In contrast, there is a coincidence for the basicity of the catalyst. It decreases from ceria to magnesia, then to silica. There is discrepancies value for alumina and zirconia. This is simply due to the fact that in the condition of the test reaction, zirconia is too much dehydroxylated. So our conclusion from this table, absence of correlation with prostate acidity signify that there is no diffusion by single H atom hopping as generally believed in the literature. If we examine the metal basicity, it corresponds also to their, of the metal oxide, it corresponds to their H2 dissociating properties, that is to their ionicity. So the order of diffusion rates of hydrogen spillover is controlled by the ionicity of the oxide support. Then the diffusion of hydrogen spillover consists in the migration of a pair of H atoms and not by the hopping of single H atoms. Now, what about the reactivity of hydrogen species? The literature statement is that the activity and the concentration of hydrogen spillover on the support are correlated for reducible support, but not for non-reducible support. This is wrong and corresponds to misunderstanding also. Hydrogen spillover is absorbed on the support weakly or strongly, and also at the interface, weakly at the interface. Ancient work, that of Teschner, Bonnell, and Miller, showed that in a hydrogenation reaction, only the weakly adsorbed species on the support or at the interface reacts, but the strongly edged species, the strongly adsorbed edge species remain as spectators. The reason is that the desorption, the temperature desorption of the strongly held species is higher, much higher than the temperature of the reaction. So the conclusion that there exists no correlation between activity and concentration of hydrogen spillover incorporated in the support for both reducible and non-reducible oxides. However, there exist exceptional cases where this correlation exists for reducible oxide, and these exceptional cases are TiO2 supported metal catalysts. The metals are poorly dissociative ones, namely silver and gold, and also in cases where the catalyst activation is conducted in inert atmosphere and low temperature. In these cases, the correlation is due to the fact that the temperature of the reaction and the temperature of desorption of the edge spillover are similar. Here in an illustration of this correlation, in the case of guaiacol hydrodeoxygenation on a silver supported on TiO2, the yields in phenolic products is proportional to hydrogen consumed by the support during the activation process. Now, what about the mechanism of reaction and the role of oxygen vacancies? I recall that after activation of the catalyst, we have conjugated pairs consisting in HOH pair, the hydrogenating sites, and oxygen vacancy or surface metal cation, which are H2 receiving sites. For metal oxide, whether they are reducible or non-reducible, the active site for hydrogenation and hydrodeoxygenation reaction are HOH pairs. For dehydrogenation reaction, the active sites are oxygen vacancies or surface metal cations. What is the role of oxygen vacancies in this condition? If we look at a reactant molecule adsorbed on an oxygen vacancy, you can see that there is no H atom in the vicinity, so no hydroconversion can exist in both cases. So oxygen vacancies may be poisonic traps in hydrogenation and hydrodeoxygenation reactions. Now, let's go to oxide-supported metal catalyst. The mechanism for the hydrogen spillover effect, it occurs with hydrogen weakly adsorbed on the support or at the interface. For reaction at the interface, the active sites are composed of oxygen vacancies or surface metal cation assisted by hydrogen species adsorbed on the metal face. Now a remark drawn from hydrogen and oxygen adsorption-desorption studies. This remark is that metal surface cations are acid-base reaction agents and stabilize strongly hydride species. Oxygen vacancies are agents of oxidoreduction reaction, and they easily abstract oxygen atoms, notably from oxygenate molecules. So this leads to conclude, to suggest that hydrogen spillover is favored by non-reducible support and with hydrocarbons as reactant molecules. As to interface reaction, they are favored by reducible support and oxygenates as reactant molecules. So our conclusion, hydrogen spillover is formed on reducible oxide by reduction followed by dehydration fastly and all over the surface of the support. For non-reducible oxide, there is HOH exchange reaction, and the extent of this exchange depend on the activation condition. Hydrogen spillover structure consists in the receiving site for H2 and hydrogenic site, namely HOH pair. As to diffusion of hydrogen spillover, it consists in the migration of two H atoms, and this migration is governed by the oxide support ionicity. There is no correlation between the activity and the concentration of hydrogen spillover on the support. This is because only H atoms weakly adsorbed on the support or on the interface are active species. And now for the reaction mechanism in hydroconversion reaction, hydrogen spillover is favored by non-reducible oxide and hydrocarbons as reactant molecules. As to the interface reaction, they are favored by reducible oxide and oxygenates as reactant molecules. Thank you for your attention.